This week we're continuing to talk about ordered collections. Since we'll be building on the work we did last week, we'll do a quick review of it. So first off, we're talking about ordered collections. So the key concept here is that data is in fact ordered. So last week we talked about the fact that this could represent a set where we've got distinct items, or it could represent a map where we've got distinct keys that map to some associated value. We're really just focused on the ordering of the data again this week, so we're not going to really worry about the map operations, but just keep in mind that everything that we're talking about could be used to create a map. We'll mainly focus on the concept of sets and basic set sorts of operations. So again, we'll assume that all of our data, our key values, represent some sort of a total order. And our basic operations are the insert operation, adding a new thing to our collection or replacing an old thing that had the same key, removing something based on its key, checking to see if a particular key is already in our collection with the exists. And since this is an ordered collection, we've got the concept of min, identifying the minimum value in our collection, or the thing that comes first, so to speak. And then the complement of that, of course, is the max operation. So adding things to the set with insert, removing things with remove, checking if something exists with exists, and min and max. Also, the one other concept that we talked about last week was the idea of iterators, are in Java some sort of an iterator function that returns an iterator object, and that iterator object is used to traverse through the collection of data. Again, Java has an interface that allows us to add this concept of iteration to different collections. So they kind of work like cursors in text. They have some sort of a concept of position, and as we reviewed last module, Java uses this in the for each style loop. It kind of takes care of the details of using this iterator object behind the scenes for you. Okay, so some other common operations. There are some internal operations that are iterator-like. So the operation will start at a location in the data structure and move forward or backwards. So a successor or next function and a predecessor or previous function will go backwards. So anyway, we've got kind of two notions here. And again, if we kind of think of the idea of iterating through something as having some sort of a cursor that has the concept of current location, we've got successor or next that move us forward and predecessor or previous that move us backwards. So last week, one of our main implementations that we concluded with was the binary search tree, or the BST. So it had a couple of different properties. The first one's kind of obvious. It is, in fact, a binary tree. So nodes can have no more than 2 children, so 0, 1, or 2 children. And then there was an order property. And this is a little bit more precise than the order property that we had with heaps. This is about the relationship between a node's key and all of the keys in its left child and all of the keys in its right child. So again, the idea here is that a particular node, which I'm going to refer to as the parent, will have a left subtree and a right subtree connected off of it. Everything that's in the left subtree has keys that we would consider to come before the parent's key. Everything in the right subtree has keys that we would consider to come after the parent's key. By the way, note here that I'm showing a less than or equal to in both of these inequalities. Since we're truly dealing with distinct keys, we could think of this as strictly less thans. If we weren't doing sets, if we were doing a collection that allowed repeat values, we could use less than or equal to, and almost everything else that we're talking about will work about the same way. Okay, so again, this induces a more precise ordering than we had with heaps. Okay, our overall goal is to get sublinear time for almost all of our major operations, and our approach is going to be continuing to build on the binary search tree. So we'll do a quick review of some of the concepts, the idea of finding data, inserting and removing data, and then the overall structure of the tree. And then we'll build off of this and impose a couple additional constraints on the shape of the tree to actually ensure that we get our sublinear operation time. Okay, so first of all, just kind of a quick review. Let's do a find operation. So given this binary search tree, first off, we should probably look at it and confirm that it meets all of our properties. So we could look at every single node, and we can kind of confirm that when we look at a particular node, it's left children, and everything in the left subtree comes before the node's key, and if it has right subtree, everything in that comes after it. So for example, 17, everything in this subtree comes before 17, everything in this subtree comes after 17. Okay, so quick review of the basic process of finding something. All of our operations start at the root. So if we want to find 19, starting at the root, we're always comparing what we're looking for to where we're currently at. 19 comes after 11, so we will go right. It couldn't possibly be in the left subtree. That's all things that would come before 11. Then 19 comes after 17, so we go right again. 19 comes before 20, so we go left, and we found our value of 19. Okay, so the find operation just descends down the tree at each node. It looks at the node's value and compares it to what it's looking for, and it's either found what it's looking for, or it moves to the left, or it moves to the right, or we've hit the bottom of the tree and we can't proceed any further. Those are kind of the four things we have to check in the find operation, or the contains operation, depending on which we're implementing. Okay, so let's talk about insert. So insert always starts with a find because we might be replacing an existing thing in the tree. So let's go ahead and do an insert of 10. So we would kind of go through the same process that we'd go through with the find to find where the 10 belongs. So it's before 11, after 5, after 9. Okay, in this case, 9 is kind of the end of the line here. We can't go to the right, so instead what we do is we create a new node to the right, and we insert our 10. Okay, important property here. Inserts create new leaves. So let's do another example. Insert in 18. So we're back to our original tree. We go through our find process again. It's after 11, after 17, before 20, before 19. So we get down here to this empty spot to the left of 19. And again, that's where we're going to insert our new value, our 18. And again, one of the important things to take away here is that insert always creates a new leaf. It's always expanding the tree at the leaves. Okay, so let's do a quick review of our remove process. So the remove process starts just like the insert process. We have to find something before we can remove it. So again, I'm going to start at the root. I'm actually going to first remove 15. So we'll start at the root. We'll search for it. 15 comes after 11, before 17. So here we've found our node. So we want to remove this thing. One of our cases is based on the number of children this has. So we either have 2 children or fewer than 2 children. If we have fewer than 2 children, we can remove this node directly and kind of bypass it and connect it up to the remaining child if it has one, or just remove it altogether if it has no remaining children. So essentially what would happen here is we would bypass the 15, and I'm going to actually write 14 in here and delete the bypassed node. So you can kind of think of that as kind of moving the node that contained 14 up in place of the 15. So you can kind of think of this node as being moved up and replacing. Okay, that's again one of our 2 cases, and really the important part here about our cases is that they're based on the number of children. If we have fewer than 2 children, we can do this process where we kind of literally remove the thing that we want to get rid of. Okay, let's look at our other case now. So we'll do another remove. This time we'll do a remove of 17. So let's search for it. It's after 11, and oh, there we are, 17. Okay, this is the more complicated case where we've got 2 children. We can't bypass this because then we'd have either the left branch or the right branch that we'd have to somehow deal with. So again, the parent is connected to a single thing. If we get rid of 17, we've got 2 things here, and if we connect it up to one of them, we're somehow omitting or dropping the other one. So if you remember, our observation was that something with fewer than 2 children is actually pretty easy to remove, and a leaf in particular is really easy to remove. So our process here is we will replace the node with something that belongs in this place. And there are actually kind of two options we could have. We could take the node, the value that comes immediately before this, which would be referred to as the in-order predecessor, or the thing that comes immediately after, the in-order successor. And we've arbitrarily chosen to go with the successor, the thing that comes after this node. So to find the successor, it'll be in the right subtree. Remember, this is all keys that come after the key in the node we're at. So it's somewhere in the subtree, but we want the smallest thing in the subtree. So we're going to go left as far as possible after we've gone right. So that's our basic process. When we're at a node and want to replace it with its in-order successor, to find that node, we go right and then left as far as possible. In this case, our left value is 19. So we'll essentially take that 19 and we'll swap it up here or move it in place of the 17. And then we can go ahead and remove the node that contains the 19. Okay, so this is our case where we have two children, and we do a swap, so we move the node that we want to get rid of and replace it with a value that logically belongs in that place, maintains our tree property. Okay, so one of the other problems we encountered was the concept of a degenerate binary search tree. The degenerate case will go through a sequence of inserts, so you might want to pause the video and go ahead and try and go through these on your own. So we'll insert 1, then 20, then 16, 4, 7, 9, 15, 13, and 10. Okay, so first off, our first node will be 1. So I'm going to go ahead and insert that. I'm going to show these without the little bubble drawing around them just to save space. Then we'll insert 20, so that will go after the 1. So I'm going to draw it over here to the right of the 1. And then 16 will come before the 20, so I'm going to draw that over here to the left. Okay, and then we'll insert the 4. By the way, I've kind of been skipping through some steps here, so again, I'd have to find where the 4 belongs. It's after 1, before 20, before 16, so 4 belongs to the left of the 16. So I'm going to go ahead and add that in here. And then we'd go through the same process with the 7, and we'd find it comes after the 4. And we go through the same process for the 9, find it comes after the 7, and then the same process for the 15, and find it comes after the 9, and then the same process for the 13, and find it comes before the 15, and the 10 comes before the 13. Okay, and I'm going to kind of show that there are all these other null pointers dangling off at all of the other spots on our tree. Okay, and the big takeaway here is that essentially at this point this behaves a lot like a linked list. Each data value is really only connected up to one other data value, and the total distance that we have to traverse could be essentially the same as our number of nodes in our tree. So to get to the 10, we have to go through all of the nodes that we've inserted, 1, 2, 3, 4, 5, 6, 7, 8 different links for the items that we've inserted into our tree. Okay, so some observations. First of all, let's think about the height versus n. So in the absolute best case, we've got something that we already saw when we were looking at heaps, kind of this idea of a complete binary tree shape where we've got something like the perfect triangle. So that's as filled in and as dense as it can possibly be, and our height is basically a factor of the log of n in that case. But the case we just saw was actually the worst case. And essentially, again, it boiled down to a linked list where our height was equal to essentially n. Okay, so this is really what determines the complexity of our operations. A lot of our operations are about climbing down the tree. So our insert operation may have to go all the way down the tree to create its new leaf, order h. Remove operation may have to go all the way down the tree to find h, or to find a particular value, or to prove that it's not there, order h. Checking to see if the tree contains a particular value, exact same. Finding the minimum value may have to go all the way down to the end of the tree, or the max might have to go down, all the way down to the end of the tree. Okay, so for our binary search tree, the height is potentially order n in the worst case. So we could think of all of these operations as order n in the worst case. So we failed our goal of having sublinear times with the binary search tree, but now we'll add some restrictions to it that will ensure that we can actually complete all those operations in log n time.